simple harmonic motion. When it executes the simple harmonic motion, the time period of simple harmonic motion t is equal to 2 pi square root of m over k. The time period of the simple harmonic motion executed by the mass attached to the spring. M is the mass, k is the spring constant. Here I am going to find the spring constant. So to find this, 2 pi is equal to square root of m over k. If you want to remove the square root, t square by 4 pi square m over k. I want to get the value of k. K is equal to 4 pi square m by t square. This is the formula I am going to use to calculate the spring constant of the spring. The m is the mass attached to the spring, t is the time period. So how to find the time period? If you set the oscillation, it is like this. X-axis you are taking t, y-axis you are taking x or y, displacement. So if you find the distance between the two peak, this gives you the time period. So the measurement of time period is difficult. It introduces a lot of error. So you are going to measure the distance time taken for many number of oscillations. So coming to this, and I'm going to load any mass as I like. This is the first schedule. I'm going to load this. Shall we load 25 gram? This is 25 gram, right? Let me add 25 gram to this. So the sensor should be exactly below this. How to check that? This is the class. So the sensor should be exactly below. We don't have any other tools to check this thing. So you are going to check manually. So keep your palm like this. If it directly hit, it will get damaged. So to protect that, keep your palm and just drop this one here. Yes. It falling here. Now let us check. Yes. Now the position of this is okay. You have to give a uniform oscillation. Just pull this slightly. Now it is oscillating. Start this. Now it is started oscillating, and the sensor record the position of this at various time. So it is recording the position, and in the y-axis you have the position. The x-axis you have the time. So we are going to take like this. Right? So take the smart tool and bring it here and merge with any one peak, right? So I am going to measure the time taken for 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up to this. So how to measure this? Take a triangle and go up to this, right? Let me check whether my measurement is perfect or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, perfect. What's the time? 5.08. At that time, you have to enter here, right? That's the time taken for 10 oscillations. The time period, this divided by number of oscillations, divided by 10, you will get this. Square this. Next, you have to increase the mass. Suppose next is about 35, right? 25, you are adding 10 more. Again, you give the oscillations. No, not good. First, erase this one. Erase this one and start the new oscillations. Now you are getting the new oscillations. Wait for 10 or more than 10 and stop this and bring the smart tool and merge it here, and again find the time taken for 10 oscillations, right? And note down the dot and repeat the experiment for various masses indicated. You are going to analyze it. Draw the graph t square versus m. T square should be y-axis, m should be x-axis. You are going to draw the graph between these two. T square second square m kilogram. We'll get a straight line. This is x1, y1, x2, y2. Your slope is equal to y2 minus y1, x2 minus x1. What is the unit? Second square per kilogram. No need to convert. What is the meaning of the slope for this graph? Is equal to t square over m. Wherever you have t square over m can be replaced. Now what is this? M over t square. K is equal to 4 pi square over slope. The K is equal to something Newton per meter. This is the spring constant of the given spring. The second part in this experiment is to calculate the gravity. The gravity can be calculated by using the Hooke's law. Fs is equal to minus kx. Fs is nothing but mg. mg equal to kx. Let us take the magnitude of it. Right? So I want to find g. G equal to kx over m. This is the formula I am going to use to calculate your g. X is the elongation, m is the mass attached to the spring, k is the spring constant. Spring constant, already you calculated it in the exam, the k will be given. So coming to the second table, this table, we have to record the position of this for zero mass. Here it should not be oscillating. Erase this. It will be a straight line. Oh, not straight line, this should be oscillating. Stop this. Suppose if it is given 40 gram or whatever the mass, just add the mass to this. This should not be oscillating. Again start this. You will get a new line. I want to find the distance between these two. So start the smart tool and bring it here and merge and bring this down. So this length gives you the x. X you can get from this. The next, add the other mass, right? Add the other mass, you will get another line. If you add another mass, you will get another line. This guy. This guy. Now you will get a straight line, right? You will get the, this is the another x.
From the top?
Yes, from the top. Now you are going to draw the graph between x over m, I hope. Yes, x over m. Going to draw the graph between x meter, m kilogram. Get a straight line, x1, y1, x2, y2. Your slope is equal to y2 minus y1, x2 minus x1. The unit is meter per kilogram. The meaning of the slope for this graph is x over m. Wherever if you have x over m can be replaced by slope. Now look at here, x over m. G equal to k into slope, meter per second square. The major source of error in this experiment could be the measurement of time period, the measurement of elongation, x. These two could be the major source of error in this experiment. Any doubt, Shiva?